Right, first I want to talk about the several bugs that in the higher physics. From now on, so I will uh, uh, prepare the three topics. The topics not uh, related to each other. That's just separated topics. And this box is just to study some things about the some very brief one instead of some continuous topic. So the first one I will discuss is adiabatic or curvature perturbation and isocurvature perturbation in the cosmology. Such density perturbations is that one of the topics in the cosmology to describe the inhomogeneities of the universe. Uh, in the adiabatic or curvature perturbation, the density perturbations is the same with the background density at the different time. So delta low at the tau is the same with the low var background density minus low var with the difference of the time. So this can be written by the low var prime delta t, where the prime represents the complement time derivative. So this is the definitions of the adiabatic perturbation. And from this, the delta tau is the same. So for all the component I or j, the relative of the delta low over the low var prime is the same. And by using the burst Friedmann equations, the low prime is the same with this form. So the ratio between the delta and the 1 plus omega, whereas omega is the equation of the state, is the same. So for example, the radiations and the matter density perturbations has a parallel relations with the factor of the 4 and the 3. For the isocurvature perturbation, it considers the difference of the component defined with Sij with the difference between the delta I over the 1 plus omega I and also for the j term. For the single build implantation model, this Sij is automatically reduced to the purely adiabatic. Some density perturbations topics, they consider adiabatic or isocurvature perturbation. The second topic is possible solutions of the mu problem. We already discussed it in the previous video, but I will review it in here. The mu problem is that the scale of the mu, which is the Susy conserving parameters, and the soft mass, which is the Susy breaking parameters, should be similar to beat the Higgs mass. And there are several possible solutions. The first one is NMSSM, which is the next the minimal supersymmetric standard model by adding the gauge singular field S. This is also the Kahler supermultiplier. And we can add additional term in the superpotential and the soft mass term. The singular field is the there's a no gauge group and no charges in the standard model, so all the possible terms can be written. Both the S, H, U, H, D can be written, and if the S get above, then this lambda S gives effective mu terms, and automatically this can have the similar scale of the soft mass scale because S the related with this soft term. And also there are possible cubic terms and quadratic terms. And also, similarly, there are positive soft terms. These terms are all the component field rather than the super field. So this is the I term, A term, B term. So two linear term, bilinear term, and the scalar soft mass term. And we can set some the massive dimension for parameters can be equal to the 0. But there is still the problem that is the NMSSM solution because there is automatically Z3 discrete symmetry, and this symmetry is just spontaneously broken when the S get above, and this makes the domain wall, which can be the dominated in the universe, and domain one problems arise. resolve this problem, higher dimensional operators that are explicitly breaking up the discrete symmetry can be introduced, or the light impulations to reduce the domain wall, and the other several solutions are possible. And in addition, in the NMSSM, the single linear components will be added to the neutral linear sector, and when we consider the Higgs potential and its minimum, the conditions of the singleness will be added. The possible second solutions of the mu problem is the Kim-Nilles mechanism already we discussed it in the previous time. This is the non-renormalizable approach with the superpotential. Also, there's at some single lab build, but the high dimensional sort of apply test with the Planck suppression. And these B's are the charges around the PQ symmetry. So this can also resolve the strong speed problems with the axiom build. So this term lambda over the m Planck scales will give them effective mu terms, and if the S it has such a boom scale, some multiplication of the soft mass scale and the Planck mass scale at the roots of this, then the effective mu terms to get the similar scale to the soft mass scale, and also this scale sort of the singular barbs is similar to the UMPQ breaking scale times the term of CB. The other possible solution is this mycelial mechanisms, which is also the non-renormalizable approach, but the Kahler potential with the Hermitian conjugates of the Kahler supermultiplet. So we can also ask the higher dimensional approach in the Kahler potential through the Planck mass suppression. The bacterial mu terms in this case is given by the lambda over the Planck with the barbs of the axonal build of the such additional singular build X. And in this case, the scale of the axonal build barb is given by the multiplication of the soft mass and the Planck mass. I'll remind that the dimension of the alpha is 2 here. The final topics we discussed is preheating. The preheating is similar to the lating after the inflation at the lating temperature. Inflaton builds are decayed to the standard model particle, and this heat the universe temperatures, and the universe tells the radiation dominant. The preheating occurs by the parametric resonance with the current oscillation of the inflaton build with the time dependence. Such a parametric resonance to make the rapidly decay of the inflatons, and the inflaton decay to the boson burst. There are no fermions decay because there's a Pauli blocking, and this to make the normalizations earlier. Let's consider some counting impulations with the quadratic terms and the quadratic term, and the Hubble friction terms makes the slow roll, and but eventually the Hubble terms ceases. So the inflaton start the oscillations at the minimum solid potentials, also depending on the sign of the quadratic terms are symmetry breaking or not. And such inflaton build pi is coupling to the boson build chi or the fermion build psi. So the inflaton can decay to the two boson pi to the chi or the decay to the fermion to the psi. And by the considering the coupling, for example, in the boson case, it will be the ZV, because the one valve of the one inflaton build get the V, but we will not discuss in the fermion in this case. For the boson decay modes, we can obtain the equation of the motion, but the K mode of the boson build chi. So this is a form with the Fourier transformation. For the K modes, there will be the expansions of the universe, such epochs and instances, and also the such scalar mixing term in Platon phi scales and the boson I scales. This helps such a term. And the inflatons oscillates at the minimum of the potential. So this gives us such harmonic oscillation form, where the capital phi is amplitudes and oscillation frequency is given by the inflaton masses. And in this case, we ignore the Hubble friction term, and the expansions of universe is just turn off. The scale factor I is a constant, and by the changes of the variable, we can obtain the Matthias equation, which is difficult form. And the solution of this differential equations has sort of one mode of the exponential instability. So the K modes of the chi build, such a boson, has exponential phase, whereas that includes the time variables here. So the such a type yield at the K mode represents the occupation number. So the particle productions are exponentially grows. And in the parameter space, we can define the sum of the Q, which is represented as the unstable parameter, and the some regions of the parameter space. The instability solutions such as exponential growth through the particle productions and occupation numbers are possible. When the Q is greater than the 1, the broad resonance is ensured, but if the Q is extremely smaller than the 1, then only the narrow resonance is okay. The Q is given by the ratio between the amplitudes of the inflatons and the barbs of the bosonic field, and in the when the preheating starts, the Q is similar or greater than the 1, so the broad resonance equivalent in the after the times the Q becomes smaller than the 1, it makes the narrow resonance, and eventually the preheating stops. And this preheating can be can be generalized to consider the by considering the non-linear term effect lambda pi for some, and the solutions of the inflaton oscillations becomes complicated due to such a non-linear harmonic oscillator form. So today we discuss three parts. The both over the curvatures and isocurvature perturbations. This will be discussed later with the density perturbation topic, and the second one will review the possible solutions of the mu problem, NMSSM, and the Kim-Nilles mechanism, and the non-renormalizable Kahler potential. And the final one we discuss the preheatings with the parametric resonance of the oscillating inflaton field.